Okay, hello everyone. Okay, this is a remake video for the fundamental problem 10.3. Okay, and why I want to remake the video for this problem because in the previous video I made, I found I have a little sign convention issue in this video, so I decided to remake the video for this problem. Okay. I want to unify the sign convention issue in the torsional load problem. Okay, so let's look at this problem. Okay, this is a torsional torque calculation problem. It say we have a shaft here. We have shaft here, and the shaft has two parts: AB part and BC part. The AB part there is a hollow section, and the BC part there is a solid section. It's solid. Okay, he wants us calculate what's the maximum shear stress in the shaft. Okay, so this is a shear stress calculation. Okay, so for the shear stress calculation, okay, for the shear stress calculation, do remember shear stress calculation? Do you remember? Do you know what's the formula we're going to use? Okay, the shear stress torsional node problem. Shear stress equal to TC over J. Okay. Okay, C is the position from the center, position from the center, or distance from the center. J is a polar moment of inertia, right? Polar moment of inertia. I'm not sure the name. Polar moment of inertia. Yes, polar moment of inertia. Okay. And from this shear stress formula, we know that the maxima always the shear force maxima is at the surface. Okay, because this formula tell you the shear stress distribute along the radius direction. So when you write, so there is a famous picture like this. Okay, if you draw this is a profile of the shape. Okay, the shear stress distribution is always like this. Okay, it's distributes increase linearly along the radius direction. Okay, radius direction. Okay, so this is shear maximum. Okay. So we already know, so when we want to know the maximum shear stress, okay, so we just calculate the shear stress at the surface. Okay. Okay, so let's back to this problem. Okay, let's look at what's the geometry of this shaft. Okay, so AB part is hollow, BC part is solid. So BC part is solid. I think there's no very special issue. Okay, let's look at the AB part. AB part it says it's hollow. Okay, so let me try. Okay, it says the AB part is hollow and the outer diameter is 80 millimeter. Okay, so let's draw the AB part. The cross section is like this. Okay, the AB part 80 millimeter. This is 80 millimeter. Okay, outer diameter is 80 millimeter, and the thickness of the wall of the hollow segment is 10 millimeter. That means, okay, for example, if this is a hollow section, and he said this part is 10 millimeter. Okay, the the thickness of the wall of the hollow segment is 10 millimeter. Okay, 10 millimeter. Okay, 10 millimeter here. Okay, and this is solid part. Don't forget it. This is solid part. Okay, so this is a cross section of the AB part. So you will know at the JAB and JBC is different. Polar moment of inertia. JAB is not equal to JBC. Okay. Okay, so the next I'm going to calculate the shear stress, maximum shear stress at the BC part and AB part. Okay, and then compare them and determine which part has the maximum shear stress. Okay, so let's say let's start with the BC section. BC section is very easy. Okay, and I want to calculate its maximum. Okay, it's T, so I need a TBC times Okay, at the surface, TC. So what's the? It's I think it's 40 times 10 to the power minus 3. Okay, it's a radius. Be careful. This line is radius, not 80 millimeter. Okay, so the J and divided by JBC, JBC, and the AB maximum is maximum. Okay, I need the torque at AB part, and times the radius. Okay, the radius is also the 40 times 10 to the power minus 3. Okay, meter. And we need divided by J. Sorry, we need to divide it by J. Okay, J. What else? JAB. Okay. Okay, we still need other information. TBC, TAB, JBC, and JAB. Okay, let's calculate. Okay, what's a JBC? JBC. JBC, it give you it give you the diameter, so it's pi over 32, 80 millimeter and power 4. Okay, I remember it's power 4. Okay. I'm not sure the value. Okay, I'm not sure the value. Okay, I'm not sure the value. Okay, let's keep it. Okay. Okay, what's the JAB? Okay, the JAB, be careful, it's not solid, it has a hollow section. So you need to, how to calculate, let's call, let me see. Okay, that means pi over 2. Okay, you have 80 times 10 to the power minus 3 to the power 4. And you have to minus the hollow section. Okay, hollow section, what's the diameter of a hollow section? The diameter of a hollow section, here is 60 millimeter. Don't forget. So here you need to minus 10 to the power minus 3 millimeter square, the power 4. Okay. Okay, let's keep it. Okay, let's keep it. Okay. And what else do we know? Okay, we still have to know the torque at the BC section, the torque at AB section. So how to get the torque at the BC section, AB section? Okay, we just use the method we are using very often. It's called cut section method. Okay, cut section. We cut the section here, and we cut section here. It's called TBC. It's called TAB. Okay, use cut section to analyze to obtain the TAB and TBC. Okay, so when we we're going to use cut section, we just follow from outside to inside. Okay, from outside to inside. From outside to inside. Okay, with the cut section method. Okay, from outside to inside. Okay, so from outside to inside. Okay, let me erase the part here. Okay, I will erase this here. From outside to inside. Okay, that means we we analyze from outside to inside. So okay, let's first draw this part. Okay, this is let me draw it. It's hard to. Okay, so this is A. I cut a section here. Okay, A here. Okay, and A here is, and here is 2 kilonewton times per meter. And okay, here is the thing. This I cut a section between A B. So there is a torque here. There is a torque TAB. Okay. And what rotation direction we should assume for a TAB? Okay, here we use the sign convention. Okay, the sign convention just in the previous video or previous slide, I just slide shows A sign convention in torsional node is use the right hand rule. Use the right hand rule. You rotate the direction. Your thumb direction is point outward to the surface. That means positive. If your thumb direction point into the surface, that means the negative. Okay. So we assume the positive. Always assume it's positive. So for torque AB, if I want to assume this torque AB is positive, which rotation I should take? But for this one, this is not positive because when you use the right hand rule, this rotation point into the inside. Okay, this rotation using the right hand rule point into the inside the surface. So it's a negative. But now we want to assume everything is positive. So what direction I should make? So I should use this direction. I should assume this direction. Okay. Okay, I should assume this direction. Okay. So when you apply the right hand rule, you rotate this direction. It's point outward to the surface. It's point outward to the surface. Okay, the surface is here. We point outward to the surface. So it's positive. Okay. And then for this section, we do the rigid body equilibrium. Okay, because the whole system is not moving or rotating. Okay, Okay, so it's statics. Okay, so sigma t equals to b0. Okay, so TAB, yeah, like I said, is positive. Okay. Well, and what is the sign for torque at the A? What is 2? Okay, use this right hand rule. The right hand rule, the rotation in this way, rotation in this direction is what's the thumb direction? The thumb direction is here. The thumb direction is here. Okay, but here is point into the surface because right now our surface is here. Our cut section is here. So you point this direction, that means into the surface. Okay, this direction is outward to the surface, and this direction is inward to the surface. So this 2 kilonewton times meter here, the sign is -2, so it's 0. So TAB is 2, and the unit is kilonewton times meter. Okay, that's a sign convention issue here. Okay. And also, this is where you have the TAB, and also we also want to know the torque for BC sections. Okay, let's do the cut section one more time. Okay, the cut section here is here. This is A. Cut section here. Here's A. Here's B. Okay, the torque is here. And the torque is here. It's 2. This is 4, and I cut a section here. Yeah, the same thing. At this cut section, we have the TBC. Okay, what direction we should assume? Yeah, we should assume it's rotates in this direction, TBC. Okay, because this rotation direction, use the right hand rule. It's point outward to the surface. That's the sign convention, positive sign convention. Okay, rotate in this direction, it's point outward to the surface, is positive. Okay, and then we do it again, summation T rigid body equilibrium equal to 0. So it's TBC. Okay, for this torque here, the 4, it's positive or negative? Yeah, use the right hand rule. You use the right hand rule, you feel your thumb direction is here. Okay, that means point inward to the surface because right now our surface is here. So this direction means inward to the surface. And for the A, the same, it's also inward to the surface. So this 4 is negative, this 2 is also negative, so it's -4 -2 equal to 0. So your TBC is equal to 6, and the unit is the same, kilonewton times meter. Okay, so here is a sign convention issue. I want you to notice that, okay, because it's very annoying in torsional load problem. Okay, so we have all the information. We have the talk BC and talk AB. So just put everything together. Okay, here just I just lump everything together in a you just lump everything together, and don't forget here is there is a kilo here. Okay, so for example, for a TBC, you need to use the 10 to the power 3. Sorry, I shouldn't use this. This color is not very good. Sorry, TBC equal to 6. Okay. Okay, so TBC here, don't forget this is a kilonewton here. So you should use 10 to the power 3 times the 40 times 10 to the power minus 3. And then JBC. JBC, I don't have the number, but just keep it and use your, just try to learn how to use the engineering calculator. And here the TAB is 2. Okay, so don't forget is you have to use to 2 times 10 to the power 3. So 10 to the power 3. Okay, don't forget the power 3 here. Don't forget the power 3 here. If you miss the power 3, your answer is also wrong. Okay, and the JAB, yeah, don't forget put this complicated JAB into your denominator. Okay. And the final answer, I think the final answer is just what in this slide show. Okay, the sigma, the tau, tau. Okay, tau BC is 59.7 megapascal. Okay, tau AB maximum is 29.1 megapascal. Okay, so here is the remake video for the fundamental problem 10.3. Yeah, that's the issue for sign convention. You should be aware of that. Okay. Okay, so here is the video. Okay, see you in another video. Bye bye.